in the chilled, echoing corridors of NASA's Ames Research Center, where the air hums with the promise of discovery, a profound silence has settled. This is a place where the boundaries of human knowledge are pushed daily, where scientists and engineers gather to unravel the secrets of the cosmos. Yet, in these very halls, something unexpected has occurred, something that has left even the most seasoned researchers at a loss for words. At the heart of the lab sits a quantum computer, a marvel of modern engineering, built to probe the universe's strangest mysteries. Its circuits, cooled to near absolute zero, once pulsed with the energy of possibility. But now, the machine has gone silent, its lights dimmed, its hum stilled. This wasn't a simple malfunction or a routine power failure. The shutdown was deliberate, calculated, and shrouded in secrecy. NASA made the decision after an event so bizarre, so unprecedented, that it sent shockwaves through the global scientific community. Official statements offered little clarity. Phrases like anomalous data signatures and comprehensive safety review only deepened the mystery. Behind closed doors, the mood was tense, the questions urgent. But behind the technical jargon and cautious language lies a story that feels ripped from the pages of science fiction, a narrative of discovery, uncertainty, and fear. The quantum computer was designed to explore the labyrinth of quantum mechanics, to simulate realities and solve equations that would take classical computers millennia to process. It was humanity's boldest step yet into the unknown. Its purpose was to tackle problems beyond the reach of any classical machine, to unlock new realms of physics, chemistry, and computation. But instead of answers, it delivered a riddle, an anomaly so profound that it challenged the very foundations of what we thought was possible. The data it produced was unlike anything seen before, defying explanation and leaving experts perplexed. Was it a simple hardware failure, a glitch in the system, or had the machine glimpsed something beyond our comprehension, something that should have remained hidden? Some whisper that the quantum computer may have opened a door to realms we are not yet ready to explore, to phenomena that lie outside the boundaries of known science. Now, the silence at Ames lingers, a modern cosmic fable, a warning echoing through the halls of innovation. It reminds us that as we unlock the universe's secrets, we must also respect the untamed power we are beginning to wield and the mysteries that may be waiting in the silence. To truly grasp what unfolded, we need to journey into the mysterious and counterintuitive world of quantum physics, a realm where the rules of reality are rewritten and the impossible becomes possible. Here, the very fabric of computation is being transformed before our eyes. Traditional computers, the kind that power our phones and laptops, rely on bits, tiny switches that can be either a 1 or a 0, on or off. Every calculation, every image, every word you see on a screen is built from these simple building blocks. But quantum computers are different. They use qubits, which are not limited to just one state or the other. Thanks to a phenomenon called superposition, a qubit can exist as both a 1 and a 0 at the same time, opening up a vast new landscape of possibilities. Picture a coin spinning in the air, not just heads or tails, but both at once, suspended in a state of uncertainty. That's the magic of a qubit, and it's what gives quantum computers their incredible potential. But there's more. Qubits can also become entangled, meaning the state of one instantly affects the state of another, even if they're separated by vast distances. This strange connection defies our everyday understanding of cause and effect. With these abilities, quantum computers can explore countless possibilities all at once, solving problems that would take traditional computers millions of years to crack. They don't just calculate faster, they interact with the very fabric of reality in a fundamentally new way, opening doors to discoveries we can barely imagine. Unlike classical machines, quantum computers think in probabilities, not certainties. Their answers reflect the universe's own logic, a world where outcomes are never fixed until observed. So, when NASA's quantum machine produced a result that seemed impossible, it wasn't just a simple glitch or malfunction, it was a sign that we had touched something truly profound. It was a message from the quantum realm itself, a place where reality is stranger than fiction, and where we are only just beginning to take our first steps. That message didn't just challenge our understanding, it changed everything, opening a new chapter in the story of human discovery and the machines that help us explore the unknown. For NASA, quantum computing was the next leap in exploring the cosmos. Their project, Odyssey, aimed to solve problems too complex for any classical computer, like plotting spacecraft trajectories through chaotic asteroid fields or designing new materials for deep space. Odyssey could analyze exoplanet data, searching for the faintest hints of life, and simulate planetary systems to reveal how common Earth-like worlds might be. This wasn't just research, it was a beacon of hope for discovery. The team at Ames were pioneers pushing the limits of computation. They expected challenges, but not what happened next. On that fateful day, Odyssey gave them an answer to a question no one had thought to ask. The unknown had arrived, uninvited. The incident began quietly, almost unremarkably, with what was supposed to be a routine simulation. The Odyssey supercomputer was tasked with modeling the warping of spacetime around a spinning black hole, a project that had been run dozens of times before. The control room was filled with the soft hum of machines and the focused energy of scientists monitoring the simulation's progress, their eyes flickering between screens filled with streams of data and complex visualizations. Everything was normal, the data flowing as expected, until suddenly, the output data stream shifted in a way no one had ever seen. At first it was subtle, a slight deviation in the numbers, a flicker in the graphs, but within seconds the anomaly grew impossible to ignore. It wasn't random noise, nor was it a system crash. There were no error messages, no alarms blaring. The simulation continued to run, but the data it produced was unlike anything in the logs. Instead, the screens began to fill with a new, perfectly structured pattern, a luminous geometric design that pulsed with an eerie regularity. It was a signal, but not one the computer should have been able to generate. The control room froze, every eye locked on the impossible display. Was it a software bug, a hardware failure, or something else entirely? The signal was layered, intricate, and mathematical, almost as if it were a language, but one with no known meaning or origin. The patterns repeated with precision, suggesting intent, intelligence, or perhaps a message waiting to be deciphered. The team scrambled to regain control, attempting to reset the system, reroute the simulation, and even disconnect the quantum hardware, but nothing worked. The signal persisted, overriding every command, as if the machine itself was determined to be heard. It was as if the Odyssey had become possessed by a will of its own, broadcasting this enigmatic pattern with unwavering insistence. The scientists leaned in, some listening as if expecting to hear a voice, others frantically searching for a rational explanation. With no explanation and a growing sense of unease, the lead scientist made a difficult decision. Fearing a catastrophic failure or something even stranger, he ordered an emergency shutdown of the quantum core. As the cooling system disengaged and the quantum core began to warm, the signal slowly faded, its patterns dissolving into static. Within moments, the display returned to normal, as if nothing had happened at all. The team was left with only minutes of impossible data, records of a signal that defied every expectation, and a machine that had done something far beyond its original design. The data was printed, analyzed, and reanalyzed, but no one could make sense of it. In the aftermath, the control room felt haunted. The Odyssey sat silent, its lights flickering in the darkness, as if waiting for another chance to speak. NASA had a ghost in their machine, a mystery that would haunt the team for months to come. No one knew where the signal had come from, or if it would ever return. But one thing was certain, the boundaries of science had just been pushed into the unknown. After the shutdown, NASA's best minds searched for answers. The first theory, a freak hardware failure. But random errors don't create elegant, persistent patterns. The odds were astronomical, like monkeys typing not just Shakespeare but a new, perfect play. A second theory emerged. The simulation itself triggered the event. The holographic principle suggests the universe's information is encoded on its boundaries. Maybe Odyssey's simulation was so accurate it tapped into the fabric of reality, reading a piece of the universe's source code. The signal wasn't a message from intelligence, but a raw data dump from the laws of physics themselves. Odyssey didn't malfunction. It worked too well, glimpsing behind the curtain of reality. The implications were both thrilling and terrifying. Then came a wilder theory, the extra-dimensional hypothesis. What if Odyssey's quantum calculations briefly opened a bridge to another universe with different physical laws? M-theory suggests our universe is just one of many, separated by thin boundaries. Odyssey might have caused a resonance, letting information bleed through from another reality. The signal's alien logic and geometry fit this idea, structured but incomprehensible. If true, this was contact with a parallel universe, a technological possibility but a profound risk. The shutdown wasn't just caution, it was a desperate act of cosmic quarantine. The team had closed a door they never meant to open. Odyssey's shutdown is more than a technical setback, it's a turning point for science. For centuries we believed our instruments only observed reality. Quantum mechanics blurred that line. Now Odyssey suggests our tools might provoke reality itself. The event shattered assumptions, forcing humility on even the boldest scientists. NASA's secrecy reflects the stakes. This isn't just a research anomaly but a potential paradigm shift. The data is classified, the team silenced. How do you reveal evidence that reality might be a simulation, or that parallel universes are within reach? For the scientists, it's both a dream and a nightmare. They glimpsed a part of the universe for which no maps exist. The silence of Odyssey is a testament to their caution, and to the unknown they've uncovered. Odyssey's silence isn't an end, but a new beginning. NASA's next steps, extreme caution, and a new field, quantum safety. We must learn which phenomena are too dangerous to simulate, and build firewalls for reality itself. The Odyssey incident adds a new variable to technology wisdom. The future of AI and quantum computing will demand not just power, but restraint. Our quest for knowledge now comes with a deeper respect for the unknown. The day Odyssey fell silent, our universe became stranger, and our journey more profound. In mapping the cosmos, we've learned the map can look back at us.